So before I go into the science, my laboratory does a number of topics, and we do work on ion transporting materials, intercalation batteries, and that's probably the reason why I'm giving these talks. We do a bit of method development because, as you will see, most of our research is theoretical, and we also explore other venues of research. So indeed, we do most of the research through the computer. There will be some experimental data that has been collected in my lab in collaboration with Professor Stefan Adams, who is also a colleague at the National University of Singapore. But let me give you some reason why going beyond lithium-ion battery is important. Of course, lithium-ion battery has set an important milestone for our society in general. Electrification of car transportation, the introduction of battery pack in our house to collect or to store energy produced by solar panel, and whatnot. Cellular phones, so all portable devices have been revolutionized because of lithium-ion batteries. What I'm trying to pitch here is that we should have alternative to lithium-ion batteries, complementary alternative that can serve specific needs, which might not be the needs where lithium-ion batteries are already implemented, at least in our society. And the reason for that has been, I'm sure some of you have been following the news, but this is a bit more quantitative, a quantitative analysis of what is the demand and production of lithium and cobalt, where lithium is, of course, the primary active ion in this battery material, and cobalt is one of the major or most important element that is utilized in batteries. For example, most of the batteries that run iPhones and Android have high content of cobalt. This cobalt transition metal is extracted from democratic, and here I put quote unquote, Republic of Congo, through often practice that are involve child labor, and market is not regulated, so oftentimes the mineral, the ores containing cobalt are smuggled to neighboring states, and so this is a geopolitically an unstable situation. Likewise, lithium. Now, unfortunately, this diagram doesn't show, but a good portion of lithium is stored in Bolivia. I believe is not shown here because Bolivia doesn't release too much of its data. But again, lithium is consolidated only in certain specific part of the planet. And here you can see Australia, Chile, and Argentina, mostly South America. That means that as our demand increases, states and countries might change their policies, right, with respect of how they commercialize or redistribute their lithium ores. So having alternatives to lithium-ion battery can complement the demands and the needs that are shown here in this graph. In particular, and I apologize here, I thought it was a slightly higher resolution when I prepared on my laptop yesterday, but there is another important problem here, right? So let's suppose that most of the lithium is sourced down here in South America, where you can see this red line. Then almost all the transformation of the material happen in Southeast Asia, in East Asia, including Japan, South Korea, and now with the CATL coming into play in China. So there is a significant, an important logistic problem whereby the materials, the ore that are extracted at various sites in the planet, also including United States, right, are then transformed in other parts of the world, including Europe, but mostly in Asia, right? So having transformation of the material nearby the location where lithium or cobalt, or this is just a map for lithium, but it's important to minimize trade costs and, of course, improve the logistic of this transformation. So All in all, I guess these two slides that I present you come to a point that we need to diversify the platform, energy storage platform available or our portfolio. And this is perhaps the most important point of my talk. So we wanted to move to other technologies, and I hope I justify that sodium ion is one way to go. With all the ramification that introducing a sodium-ion battery technology has compared to a lithium-ion battery technology. There are two points of strength that I wanted to emphasize when it comes to sodium-ion. Sodium is ubiquitous, is available in seawater, perhaps. It can be extracted from soda ash, and there are a number of deposits scattered on the planet, in particular here in the United States. And a second point of strength that has nothing to do with energy density. All of us know that a sodium ion cell with the equivalent volume of mass of a lithium ion is much less energy dense than a lithium ion equivalent. But another point of strength is that in sodium ion batteries, you can use aluminum current collector, right? This might sound trivial from a laboratory perspective, or a situation where batteries are made in the laboratory, but are made in laboratories. But from an industrial perspective, moving to aluminum over copper has a significant decrease of costs and perhaps even weight. Now, there are a number of companies, and here I forgot the CATL. CATL in China has announced that they have a commercial sodium batteries. I think not many have seen them, but is not shown here. But there are some old player here, Faradion, by far the most advanced, or at least in terms of age, sodium-ion battery companies, and older players such as Tiamat, which is a company based spin out of LRCS in France, and connected also to some of our research work that I will show you. And since some of you in the audience are interested in solid states, I just want to remind you that indeed the solid states is a phenomenal avenue for fundamental research, but while it's intriguing from a fundamental perspective, because there are a lot of things to be a problem to be solved, indeed it comes with a share of issues that needs to be addressed before this technology can be commercialized. And here I just wanted to show you that, for example, the interfaces or stabilizing heterogeneous interfaces or solid-solid interfaces, where solid could be the solid electrolyte display here as a marble type of texture, and lithium metal anode or sodium metal anode, effectively. Of course, there are also some design advantage which one can tap on when using a potentially working all solid state battery, is that you can utilize current collector, but this current collector, if appropriately designed, can accommodate stack configuration in this sodium all solid state battery. I will now alternate between all solid states and normal battery, in which Nasicon has been studied. So this is a Oreo battery, and it's called Oreo because, of course, is reminiscent of the Oreo biscuits. And this has been developed together with our French colleague at LRCS. In the Oreo schematics, the two layers, the brown or black layer that you see here, are effectively composite of carbon and sodium vanadium phosphate. So in here, we use, in forming these electrodes, positive and negative electrodes, we use two different state of charge of sodium vanadium phosphate, which is a Nasicon by all means. The white part, so the cream in the Oreo biscuits, is sodium zirconium silicon phosphate, which is the John Goodenough, the first material, the Nasicon, that has been discovered many, many years ago by John Goodenough. Now, the beauty of this battery is they are monolithic, right? Monolithic in the sense that one, you form them into a spark plasma sintering machine, right? So you deposit a composite, as you can see here, of MVP, which is sodium vanadium phosphate, together with some carbon black and some sodium, zirconium, silicon, phosphorus, Nasicon with formula that you see down here or up here, general formula. And all together you form this initial pellet in the spark plasma. Then you deposit the powder of NSSP, which is the Nasicon separator solid electrolyte. You perform a second sintering, and then you perform a third sintering, which you fuse all the three materials, forming the Oreo battery. So in this sense, this battery doesn't require any pressure stacking. And the interesting part of this all Nasicon battery, whereas, as you will see, it will have a very limited energy density, is that because you get to work with Nasicon on all the three different layers, the two part of the biscuits and the filling cream in between, the lattice mismatch between the lattice, since all these Nasicon share similar crystallographic feature, the lattice mismatch is really reduced. Of course, our groups have been working for a while in optimizing also the sodium metal Nasicon, because it's interesting from a fundamental point of view, interfaces, and as well with other positive electrodes. So here we use both MVP, but also MVPF, which is a higher voltage electrode when you start fluorinating a Nasicon material. It's not a Nasicon structure, but you can see it as a fluorinated Nasicon material. But let's describe briefly what is the Nasicon structure, right? And the complexity that comes with the Nasicon structure, as it will also be useful when I describe my computational model or the stuff that our group has been researching, right? So Nasicon comes with a skeletal structure that is constituted by transition metal octahedra, and that are indicated here in gray, right? This octahedra can be occupied by zirconium in the nominal composition produced by Hong, the assistant of John Goodenough many years ago. But as I said before, you can substitute zirconium with open shell 3D metals such as titanium, vanadium, chromium, iron, or not. You can, in principle, exploit almost the first row of transition metal. These octahedra of transition metal are then corner sharing with this tetrahedra that you see here in blues in different representation on the left-hand side and on this magnification on the right-hand side. And these tetrahedra can either be silicon, phosphorus, sulfur, and in the Nasicon that we will see in this talk is mostly silicon and phosphorus, both at the level of the electrodes material and the solid electrolyte. And as a result of this skeletal structure constituted by the interaction of this transition metal octahedra and the tetrahedra of silicon and phosphorus, interstitial sites are created, and two types of sodium, one type of sodium indicated in red called sodium 1, and one type of sodium indicated in silver here, sodium 2, are formed. Now, the interchange between sodium 1 site and sodium 2 sites is the driver of ion transport in this material. Of course, you need a vacancy, so the vacancy is introduced, or a number of vacancies. Vacancies are introduced by tuning the ratio, at least in the solid electrolyte, between silicon and phosphorus. Okay, the more silicon you introduce, the less vacancy you introduce, the most phosphorus you add in this tie line that goes from x equal to 0, meaning 1 sodium per formula unit, to x equal to 3, meaning 4 sodium per formula unit. You can explore all sorts of silicon and phosphorus composition. Before I'll go to the electrolytes, let me tell you something about the electrode material and the puzzle that has been ongoing, or the big question that has been ongoing on this sodium vanadium phosphate, and which I will try to elucidate in my slides. So this is a voltage curve, right? That you can compute from first principle calculation. I don't go in details on how the first principle calculation have been done here, but for the most experienced people, you can see two lines, the blue line and the orange line. There are two different level of approximation in which we use first principle or density functional theory calculation to approximate the voltage curve. But if you don't trust the theory, well, you have the experimental voltage curve here, which is shown here by this dashed green line. Now, what happened in this material? In this material, as you can see from an experimental standpoint, you can take 4 sodium out. If you start from composition, sodium 4, vanadium 2, PO4 3 times, you can extract all the sodium all the way to the sodium 1 composition. So to this composition that you see below here. Of course, from theory, we can also predict the energy or the voltage involved to the extraction of the last sodium, meaning going from sodium 1, this position here, all to sodium 0, meaning extracting all the sodium. And this, in practice, is possible, right? Because it's enabled by the charge states of vanadium. So here you can see, in fact, the reaction that we want to try, and this is done in the last step of the voltage curve from sodium vanadium phosphate with 1 sodium per formula unit, where all the vanadium are 4 plus, right, or plus 4. We wanted to exploit the vanadium 4 to 5 plus redox couple, and of course, this entails the extraction of all the sodium ion, right? This, of course, has been tested and experimented for many, many years, but nobody has been able, at least with the traditional synthesis of sodium vanadium phosphate, to extract the last sodium. And this is important, right? Because when you go from sodium 4 to sodium 1, you can access a capacity, and here I'm using a bit of a battery jargon, of 168 milliampere hour per gram. But if you were to access the last sodium, you could have a 56 milliampere hour per gram. And so to reach indeed a theoretical capacity of almost 224 milliampere hour per gram, which looks quite competitive, right? Especially when you're operating at such a high voltage, at least, believe it or not, the prediction around above a 4-volt versus a sodium reference, right? So my students, Ziliang, now at Northwestern University, is doing a postdoc there, developed this kinetic Monte Carlo code, which enables us to study the transport and how difficult it is to indeed extract sodium from the vanadium phosphate electrode. So as you can see here on the graph that I show, on the bottom line, on the bottom axis, right, we show composition. So we go from sodium 1 all the way to sodium 4. We don't show sodium 0. And what we are plotting on the y-axis is the jump diffusivity. Without going too much into detail on what is the jump diffusivity, is the diffusivity of the sodium ion as you extract it from the material. So what you can see is that first of all, there is a peak in this diffusivity, hitting more or less 3.0, right? Or the area around composition slightly below 3.0 and 3.5, and slightly below 3.5. This is the best situation, at least where sodium ion are fastest to transport or quickest to move into the lattice of Nasicon. But as you extract sodium, start extracting sodium ion, going all the way to composition 1, the diffusivity drops significantly. And when I say significantly, we are talking about 3 to more than 3 order of magnitude. Remember, this is a log scale, right? Now, there is, so this is substantial. It tells you basically that extracting the last sodium, if you were to go below one X1 per formula unit, would entail having heating diffusivity that are even lower to 10 to the minus 14 in this unit of centimeter per second. There is a normalization that is being done here. If you're interested, we can discuss about it. But the second phenomenological aspect is that extracting, I told you there are 2 sodium sites, right? One sodium site is octahedrally coordinated, and the other sodium site has a higher coordination number. But what happens is, as you start extracting sodium from a situation of sodium 4 all the way to 1, you can see that almost all the sodium is extracted from the sodium 2 site. So, of course, there is an exchange between sodium 1 and sodium 2, but all the sodium is extracted from sodium 2, and here we are tracking basically the population of that sodium site. So the last sodium is confined, the last sodium is of type sodium 1, so the octahedrally coordinated sodium. So extracting the last sodium effectively is the really bottleneck, and extracting the last sodium, which has character of sodium 1, so octahedrally coordinated, seems to be the crucial point here. If you look at the phase diagram, and this is the predicted phase diagram from our group, we use, of course, the density functional theory, cluster expansion, Monte Carlo. We have expertise in this area. Appears much more complicated than our experimental colleagues thought. And this has been driven the next experimental step. This is so a success story where theory has been applied to understand in detail this material, and there are some revelation that comes out from this theoretical calculation that then are implemented into understanding some experimental aspects. So what you see in this phase diagram, again, the composition axis tells you how much sodium you have, and here on the x-axis, the y-axis, we have a temperature. What you can see here is that there are regions of indicated with this Greek letter of phase separation. So between 1 and 2, we have phase separating region. This is, in fact, aligned with the plateaus, right? Between 1 and 2, you have a phase separating region, and this is also expressed in the experimental curve. And you also have a second plateau between 3 and 4. This is indicative of phase separation, right? And so between 2 and 3, 2 and 3 and 1 and 2, we have two different two plateaus, right? Effectively, or just one plateau. However, the phase diagram here reveals that at x equal 2, meaning 2 sodium per formula unit, there is a new single phase. So you have a line compound here, right? And this line compound was never reported experimentally. So, of course, when you see such a thing, you start believing the theory is wrong, right? As usual, but I will demonstrate the theory maybe this time as something to say positively, right? And these are the voltage curve that we predict. Again, the thick line are the voltage curve predicted as variable temperature with our Monte Carlo machinery. And the experimental, this is an old experimental voltage curve predicts a flattish plateau between 1 and 3, right? And of course, here we have a single phase region in this area, which is identified by the single phase region compound in the material. So here the voltage curve is flat, you don't see this step, so what's the deal, right? So now if you prepare, so this gave a hint to our experimental colleague. Well, they said, if from the phase diagram, the theory people sees a single phase region at x equal 2, well, it's maybe possible that if we combine at high temperature a synthesized Nasicon at composition 3 and a synthesized Nasicon at composition 1 at high temperature at the proportion of x equal 2, well, we might be able to form this phase. And indeed, they went to the lab and they were able to form this line compound material. Long story short, when you take this line compound material and start extracting sodium from 2 to inferior quantity of X and then try to reintercalate sodium, what you get, actually, sorry, I wanted to say that they see now the sodium 2 phase. So these are XRD synchrotron, apologize, operandum synchrotron done by my colleague Christian and Sun Q Park. You can see that when you do the operandum synchrotron measurement, as you indeed cycle the battery, you will see strong signature of the sodium 3, meaning sodium 3 formula, sodium 3 sodium per formula unit, 1 sodium per formula unit appear, but there is also signature of the existence of the sodium 2, so the line compound that we observed computationally. So then they went to the lab. As I said, this is the one that they discovered by extracting the sodium from sodium 2, but they can go to the lab and really reproduce the phase diagram, right? They take the sodium material at X equal 3, they take the sodiated material at X equal 1, they work at the proportion of X equal 2, they combine it at high temperature, they make the synthesis, and they get a new sodium 2 phase. And now, look, discharging from the sodium 2 phase, they can effectively extract all the sodium ion from this MVP O4, effectively achieving what we were trying to, what I was trying to show you from a theoretical perspective and theoretical capacity. So there are ways in which you can synthesize this material, and depending on which phase you start, you can access capacities and extracting all the sodium, which is quite intriguing. We don't know all the phenomenological aspect. Of course, I show you from theory that extracting the last sodium synthesis, the bottleneck, it might be, there might be explanation that I can give you. We have a paper in submission and, of course, a patent that has been deposited. Now, let me switch gear a little bit, and this is more about my research on the electrolyte side business of this Nasicon material. Again, Nasicon is very versatile in terms of composition. Here we are looking at Nasicon where there is zirconium as the transition metal, so closed shell transition metal. And depending on the sodium composition, you can have different phosphorus or silicon, or depending on the phosphor silicon content, you can have sodium vacancy, availability or lack of sodium vacancy in this material. Again, bringing you back to the picture of solid-state battery and the Oreo battery, we are talking about the material, the filler in the Oreos biscuits that are depicted here. Now and again, I will refer to this as an ZSP because it's easier to address, but what we have done is, again, using computational material science, we could predict the phase diagram of this material. And just to give you push a little bit why predicting phase diagram from first principle calculation is very important to experimental colleagues is I wanted to emphasize that over 40 years, only a handful of composition, which are shown here as stars, right, on this phase field, right, have been studied and investigated from an experimental perspective. So providing you a full picture or a full picture of the phase field of this complex material, in particular Nasicon, but other material, is quite important because it can enables you to tune what are the area of interest in the chemical space you're interested in. Okay, let me address the ion transport in this Nasicon material, and now we combine our phase diagram prediction with our kinetic Monte Carlo code. As we said, ion transport is still an important aspect to be addressed in solid-state ionics, and in particular in solid-state electrolyte. And Nasicon was chosen here because it's a well-studied material, and we wanted to develop effectively a new technology to address ion transport in a different way than is done on a regular basis in this field. So there are two a question that I will try to address in this final part of my talk. The first question is, do we understand the effect of mixing of polyanion of ion transport? So most of fast ion conductors that have been reported in the literature, not only for sodium ion material, but also mostly for lithium ion, are composed by polyanion solid electrolytes. So all Nasicon, the LGPS material contain GSE4, SNSE4, thiosilicate, thiogermanate, thiostanate, and this is therefore, and these units are randomly mixed in the lattice, the anion lattice of the system. And of course, Nasicon is no different from them. It's also a random distribution of silicate and phosphates in the matrix of zirconate and sodium and vacancy. So the question, the fundamental question here that we posed is, or the hypothesis is Nasicon or is the disorder of the polyanion species driving transport? The second aspect that maybe some of you are interested is that there is a large variability or report ionic conductivities. And here we are talking about ionic conductivities that have been reported over many years at different temperature for this Nasicon composition where sodium, the sodium content is fixed at X equal 2 or 3. You can see that given a composition, right, and a temperature at which measurement has reported, there is a large or significant variability of the conductivity that is reported. So I will try to show you that maybe computation can be helpful or theory in that sense. Again, let's relook at the structure of this Nasicon. I will show this structure from a slightly different perspective. I told you there are two types of sodium. Now the attention should be on the sodium. There is the sodium 2 type of sites. These are these gold ions, and the silver balls are the sodium 1 structure. And what I indicate here as red balls are either silicate, meaning SiO4, or PO4 units. So I can simplify the picture and I can look at this hexagonal or pseudo-hexagonal prismatic hexagonal prism unit that I can see here, where the six of the corners are sodium 2 ions, and one of the sodium 2 ions, and the central ions indicated in gray is the sodium 1 ion. And as I told you, in Nasicon transport occurs between a vacancy ion exchange between sodium ion and sodium 2 or vice versa. Now, what we want to do is to try to study the transport of the sodium ion going from sodium 1 to sodium 2 or vice versa as we change the composition of the silicate and phosphate. And so we have done it, right? We compute all the migration barrier in this unit cell, which we call prismatic or migration unit, right? So what I'm going to show, what I'm showing you in this graph is this map plot, and this map is constituted by it has a lot of information. So what I'm changing on the x-axis is basically whether these red ball are vacancy or occupy lattice, right? So when you see 0 here, it means that the orange ball are all vacancy, right? And when you see 6, all the 6 balls are occupied by sodium side. Likewise, I can do the same thing with the silicon phosphorus ratio, where you see 0 here. It means that all the red balls are occupied by phosphate, and at 6 here, it means that all the red balls are occupied by SiO4 units. And now we plot how the migration barriers evolve as we move from 0 sodium on the sodium 2 lattice and all phosphorus. So this is a terrible barrier, is above, I apologize here, the units are electron volt, above 600 milli-electron volts. And this is well aligned with experimental, my estimation of migration barrier at this sodium composition. And when we go at very high silicon content, meaning that here is 6 and very little amount of vacancy, the barrier become very, very low. And of course, we can use now our model. These are computed barrier, but there is a model in between, a cluster expansion, and we can compute all the barriers at different composition of sodium vacancy, or the sodium 2 sites, and silicon phosphorus vacancies. All right, and you can see you have a variety of situations. We use this model, which is fast to compute now. It doesn't rely on first principle calculation anymore, because it can. This model can predict the migration barrier of sodium at any composition in terms of silicate and phosphate in this unit, and sodium and vacancy. And we use this model to drive kinetic Monte Carlo. What kinetic Monte Carlo enables us to do is that we can measure the conductivity, right, at various temperature, and this is indicated by different color lines here, and at different composition. So what comes out here is that at composition 2.4, meaning that you have 3.4 sodium per formula unit, you have a peak of ionic conductivity, right? As you decrease the sodium content and you go to x equals 0, meaning 1 sodium per formula unit, the conductivity tanks, and this is well aligned with phenomenological experiments. And as you increase the silicon amount in the material, meaning that you limit the number of vacancies to the point that there are no vacancy almost, the transport decreases likewise. The beauty of using kinetic Monte Carlo in comparison to MD is that, one, you capture fully the correlation between sodium ion and sodium vacancy. And second of all, because of the nature of Monte Carlo, you describe the random distribution of the silicon and silicate and phosphate and sodium and vacancy fully in your model. This would be a daunting task, a very daunting task if you were to do molecular dynamics. But what comes out from this study is that you can identify that the highest conductivity is reached at sodium 3.4, right? And here again, Monte Carlo simulation can be applied through our code that we have published. And if you are interested, this is an open source code. I would invite you to utilize it or contact us if you're interested. The beauty of that is that you can do huge simulation, right? We are reaching here 1 million atom simulation, and you can do it on your laptop as long as you have a cluster expansion Hamiltonian that enables you to do that. The second aspect that is very important is not only the size of your simulation, but the time that you can reach, right? Here with Monte Carlo, we can really coarse grain large time landscape and reaching millisecond time simulation. And now let me verify that these theoretical predictions are not so crazy, and I will be done after that. We have prepared Nasicon both in our laboratories and in the laboratories of LRCS. We've also been in contact with the laboratories of Olivier Guillon and Chan Nima at ULIS in Germany. So we've been in contact and also exchanging samples with them. So they are also been our collaborator here. And what we are trying to design is a synthesis of Nasicon, which is zirconia-free. As you will see in the reminder of the talk, the last few slides, Nasicon, if you don't take a precaution in how you synthesize this material, and here I must admit I'm a little bit out of my depth, you can have zirconia, monoclinic zirconia, as one of the material that is formed into during the synthesis. And zirconia, having monoclinic zirconia, is not detrimental, but of course change the morphologies of your grain boundary, changes the temperature of sintering, might have direct impact on the conductivity. And so here are some XRD, that have been done a measure on compound in which we remove systematically some aliquots of zirconia during the synthesis of Nasicon. So L0 means that we do synthesize the material at the nominal composition using the nominal stoichiometry that you will get. L5, L10, L15, and L20 means that we remove a fraction of Nasicon into of zirconium oxide precursor during the synthesis. And as you can see, as you start removing systematically some of the zirconium from your precursors, when you hit L15, meaning that you have removed almost 15% of the required zirconium, you can entirely eliminate zirconium oxide, at least from a Raman and here X-ray diffraction perspective. Now we can measure the conductivity of this sample, and we've been using cryostats, right? We've been using a cryostats that enable us to reach low temperature. This is to isolate the grain boundary from the bulk conductivity, also because our measurement that we do from theory are bulk transport, right? At least 1% here. And so it's important to separate the bulk transport from the transport affected by grain boundary. And here you can see the two samples, right? I show you the L15 and the L0 sample. It's phenomenal to see that when you have a reduced amount of zirconium, in fact, no zirconium, at least detectable from XRD and Raman spectroscopy, you can do a zoom in of here, the grain boundary structure becomes very, very different or much less prominent compared to the, here there is a switch in label. I think there is some confusion in this plot. I should not comment it, but L0 basically, so the grain boundary amount, if you zoom in L0 compound, which is the compound with zirconia, is so large that when you zoom in, it becomes basically invisible, and the grain boundary proportion of L15 is significantly reduced. So controlling the zirconia amount in this dense pellet is crucial to ion transport. And here are some other measurements. Here we have changed the composition. Sorry, here is to prove you that the sodium 3.4 composition that has been detected through theoretical experiment or measurement is indeed very fast from an experimental standpoint, right? The bulk conductivity reaches 11 millisiemens per centimeter, and this is by analyzing the low and high temperature conductivity of this material with this equivalent circuit, so impedance spectroscopy. And of course, the total conductivity, which is affected by grain boundary, is downsized by almost 50%. So we are reaching 5 millisiemens per centimeter. Not bad, indeed. We have been cycling some of these batteries. These are all Nasicon battery, the Oreo battery that I've been showing you. These are really preliminary data because it's difficult to optimize this material, but it's important to see that there is a lot of optimization that needs to be done if we wanted to really have this battery prototype to work. I don't think they are useful from a standpoint of energy storage because they are cycling at high temperature, as you can see, 200 degrees Celsius, and the capacity that you can extract is very limited. But certainly, I show you some interesting result on the sodium vanadium phosphate that can be used in traditional liquid type batteries, right? And with our carbon and more commercial solid liquid electrolytes. Kinetic Monte Carlo is interesting because in addition to giving you transport properties such as conductivity and diffusivity of the materials, which is definitely good and address the point that we need to have highly correlated conductivity and capturing the transport and the random phenomena of distribution of silicate and phosphate or polyanion generally in some electrolytes, but it also can give you information about what is the percolation, path that the ion, sodium ion takes into this very different composition. So here I'm showing you some snapshot of the kinetic Monte Carlo at different compositions: sodium 1.3, sodium 3.95, 7. So sodium 3.9.7 mean high silicon content. And here you can see most of this cell, the prismatic cell, are violet because there is a small sodium ion transport activity, and there are some isolated red, meaning that there is high frequency there. These are active cell, but because the red are diluted in the violet, there is effectively not a lot of percolation channels. When we go to the fastest ion conductor, sodium 3.4, you can see that all the red boxes or prismatic cell are connected to each other. There is a lot of activity, and of course this determines path of percolation for sodium ion. So in conclusion, from a theoretical standpoint, I prove that kinetic Monte Carlo approach provides an alternative to molecular dynamics that is mostly used in the battery community. It enables you to provide a statistical view of the random distribution of polyanion, but also sodium and vacancy in the material. In addition to that, it fully captures, kinetic Monte Carlo is able to capture the sodium-sodium and sodium vacancy correlation, which is something that is very hard to compute even with the classical molecular dynamics simulation or machine learning-based molecular dynamics simulation. And from a scientific point of view, I demonstrated that silicon content in Nasicon solid electrolyte, high silicon content material are preferred. And this has been also shown recently by the CEDAR lab at UC Berkeley. In summary, I hope I can demonstrate that theory is an important tool, and theory can do a lot. This is theoretical, especially when in a framework of multi-scale simulation, where not only DFT is used, but layer above DFT are implemented. And I show you some cases of experiment that have been very important to our lab to not only facilitate comparison theory versus experiments, so validation, but also I showcase situation, especially with the sodium vanadium phosphate, but also the Nasicon electrolyte, in which theory can inform some dedicated experiment. And with that, I would like to thank you all for your attention, and thank the member of my group. Some member have left, and I will be happy to answer any question. Thank you very much for your attention.